I'm going to talk about the graphs of the tangent and cotangent functions. So give me a minute to draw the graphs of the tangent and cotangent functions. All right, so the blue curved segments represent the graph of the tangent function. And these purple curved segments represent the graph of the cotangent function. Okay, now I'm going to be using the terms amplitude and period. So if you don't know what those terms mean, I would invite you to watch my video that introduces the graphs of the trigonometric functions where I define what amplitude and period are. All right? So as with the sine and cosine graphs, we can determine a lot of information from the graphs of the tangent and cotangent functions. All right. First of all, notice that it looks like there's a portion, and it looks like someone made several copies of a certain portion over and over again, and to construct both graphs. So because it's made of several copies, we say that the graphs are periodic. And I hope you can see that the period of both is pi. Okay? Now, the graphs extend indefinitely upwards and downwards, so the ranges include all y values. Okay? The graphs also extend indefinitely to the right and left. However, there are certain points that are not in the domain. That's because there are vertical asymptotes. Okay? For example, the blue curved segments do not include the points with respect to x equal plus or minus pi over 2 or x equal plus or minus 3 pi over 2. Those x values correspond to the vertical asymptotes. All right, so we say that for the domain of the tangent function, it includes all x values except plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on. Okay? Now, the cotangent, the curved segments of the cotangent function, notice that they don't include the points with respect to x equal to plus or minus pi, nor with respect to plus or minus 2 pi. So for the cotangent function, we say that the domain is all x values except for plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and also 0 pi. So we actually have to include 0. Or we have to exclude 0 from the domain of the cotangent. Okay? Now, we can't say that the graphs are identical except for a horizontal shift. So we can't define a phase shift with respect to tangent and cotangent. However, there is a different relation. There is a transformation to go from tangent to cotangent. All right? Notice that if you take the tangent graph, you reflect it with respect to the y-axis, okay, and then you also shift it to the left by pi over 2. Then the tangent graph, the points of the transformed graph will be right on top of the points of the cotangent graph. All right? All of that is to say that, let me write it at the bottom of the board, the cotangent of x is equal to the tangent of minus x plus pi over 2. Okay? So that corresponds to the reflection about the y-axis and the necessary horizontal shift to turn one graph into the other. All right? And so that identity, of course, is the complementary angle identity. Okay? So all of that information can be discerned from looking at the graphs. Okay, so now let's discuss some other transformations of these functions. So what does the graph of tan tangent of x look like? Okay, so the period will still be the same, and we didn't have an amplitude before, we're not going to have one now. All right, the effect of the 10 is going to be to stretch the graph vertically. So give me a second to show you what that looks like. Okay, so it's still going to have a vertical asymptote with respect to x equal plus or minus pi over 2, but it's going to shoot up faster. Okay, so maybe I can draw it going up faster as you move to the right. Okay, and then likewise at pi. All right. All right. Now let's discuss this one. So what would the graph of the tangent of 10x look like? Okay. So this time the period is not going to be the same as with respect to a regular plane tangent function. So let me show you what the graph looks like for this one. And here is one way to see where the x-intercepts are. So we know that the tangent of 0 is 0 and the tangent of pi is 0. So 10x has to equal, or if 10x equaled pi, then the tangent function would be 0. So its tangent is 0 with respect to x equal to pi over 10. Okay, so that can help you to make the graph accurately. Okay, so the graph will look something like that. Okay, now if you were to do an analysis of how different coefficients in front of the x affect the period, you would notice that the period of the tangent of kx is pi over k. Okay. Now, however, I don't necessarily require you to memorize that, because you can simply derive it on the spot like I did using similar reasoning. Okay? All right, now let's do this one. What about 10 plus the tangent of x? What would the graph of that one look like? Well, the period for this one would be the same as for a regular tangent function. And the graph would be shifted vertically. That's the correct transformation. So we're still going to have the same x-intercepts. However, we're going to have different y-intercept. The y-intercept is going to be with respect to 10. All right, so something like that. Okay. Now, I would like you to try to graph a transformation of the cotangent function. Would you please pause the video and graph 1/10 times the cotangent of x if you can. So do that now, please. All right, so I'll go ahead and show you what that looks like. So the period is going to stay the same as with respect to a regular cotangent graph. And what's different about this one is that it's compressed vertically with respect to the vertical direction. So that would have the effect of making it look something like this. You see how it looks like it kind of is pushed towards the x-axis? Okay, give me a minute to finish my sketch. Alright, so something like that. Okay? Okay, now would you please graph the cotangent of 9x? And also determine the period if you can. So pause the video and do that now. Alright, so I'll go ahead and work it out as well. So give me a minute to draw a graph. Alright, so that's what the graph looks like, and the period is pi over 9. In fact, doing a similar analysis to the analysis for the tangent function, you could determine that for the cotangent of kx, the period is pi over k. All right? Now, you don't necessarily have to memorize that, because you can determine the period in other ways, such as by solving for various x-intercepts, and the distance between the x-intercepts will also give you the period, consecutive neighboring x-intercepts. Okay? Alright, so for our last exercise, would you please graph 5 plus the cotangent of x? So pause the video and do that now, please. Okay, so I'll go ahead and work that out as well. Now, the period is going to be the same as with respect to a regular old cotangent graph. The 5, this specific transformation doesn't change the period. The effect of the 5 is to raise all the points on the graph up a distance of 5. Okay, so something like that.